plan for today is to continue working with second order differential equations with constant coefficients. And what we need to think about, last time we were working with these types of differential equations, and we were pretty much sticking to the situation where the roots were real. And so what I want to talk about today is what do the solutions look like when our characteristic equation has complex roots. So before we get started with that, are there any questions anybody has? I just want to point out a couple of things on Canvas. Let me just share that. One is I put up the solutions to first couple of homework assignments. I kind of delayed it on purpose just because I want to give people a chance to try and correct their work before seeing the solutions. But if you're curious about where to find the solutions, if you click on the assignment, homework 1, now you can see the solutions are posted there. So right below where the original PDF was, you can find some solutions. You can check your work on that. In addition, I added a early semester course evaluation. It's 7 multiple choice, multiple selected, maybe 3 or 4 open-ended questions, just on feedback about how you're finding the course, what materials are helpful, what sorts of things do you think I could do to help, that sort of stuff. So these are anonymous, so feel free to share your open thoughts. I won't know who says what, and if I get an 80% response rate out of the entire class, then I'll give 2 bonus points to everybody on the first exam. So your feedback is definitely really helpful to me and to your classmates. So please give that a look. Right now I have it set to close on Monday at midnight, so the same time your homework is due. But you can find that in Canvas. Otherwise, if you have any questions about how the homeworks are being graded, please just let me know. If you think that you're not sure why you lost points or something like this, I'm happy to take a look at whatever the grader might have done. So just let me know about that. Any questions related to the general things before we get started today? Okay, so great. So far, okay, so just to kind of review what we talked about last time. So we were talking about solving second order differential equations with constant coefficients. In particular, we're going to consider the case. Can you guys hear me? Can you just give me a thumbs up? Okay, I'm getting like a weak internet signal warning. Okay, and so we were focusing on the case just when we have a 0 on the right side, so what we would call a homogeneous differential equation. And so the way that we talked about solving these last time is we said, well, it makes sense to guess that exponential things might be solutions. And when we do that, what we see is that e to the RT is going to be a solution for any value of r that is a root of this characteristic equation. And then we talked about, okay, if we have 2 repeated roots, then after I find these 2 values of r, we've got our general solution. If we have one repeated real root, then we have to modify that solution a little bit. And so then the question is, well, what do we do when we have complex roots? So let me just kind of put up a couple of examples that maybe can motivate us. So for example, if I were trying to solve a differential equation, such as this one, just to kind of review the process we went through last time, then what we would do is first set up the characteristic equation. right? Just by pulling the coefficients from the differential equation down to the corresponding quadratic equation. Then we would try and solve that resulting equation. In this case, we can factor it. And then we see that we have two distinct roots, -3 and -2. And then from that, we would get our general solution is C1 e to the -3t, C2 e to the -2t. So that's a quick recap of the process we talked about last time. Any questions? Feel free to chat or just talk them in, raise a hand. Okay, and so now what happens, what I want to consider is, let's say we had one that looks like this, y double prime minus 6y prime plus 10y is equal to 0. We want to solve this same idea, right? We pull the coefficients from the differential equation to the corresponding characteristic equation, and then we would try and solve this. And this one doesn't factor. So using the quadratic formula, we would get minus b plus or minus the square root of b squared minus 4ac, which in this case would be 4 times 10, all over 2a. So by the quadratic formula, we can try and track down these roots. This gives us 6 over 2 plus or minus the square root of minus 4 over 2. So here our roots are 3, and when we take the square root of a negative number, right, this would give me 2i. So these would be an example of a situation where we have complex roots. So in this case, we would get 3 plus or minus I as the roots here. And so the question is, well, what can we do with those sorts of things? How do we make sense out of something like 3 plus e to the 3 plus it, right? If we try and mimic the solutions that we had over here when we find the roots with complex things, then we need to make sense out of what happens when we take e and raise it to an imaginary number. So that's the goal for today, is what can we do with things that look like this? Any questions? Okay, and so the solution to this dilemma is exactly figured out using Taylor series. That was the point of having you take a trip down memory lane with Taylor series. So let's consider, so we have this, we are gonna have to deal with things that look something like that. And let me just say this, just using properties of exponents could be broken down like this. So it's not the real part that we need to worry about. That makes sense. It's what do we do when we have an I in the power. So let's consider like the most general case of this, which is if I had something like e to the I beta times t. So this letter here is the Greek letter for beta. So as you saw in the video or practiced on the reading quiz, let's try and set up the Taylor series for e to the I beta t, which means we're going to need to use this formula down here, which means we're going to need to find and evaluate first, second, third, fourth, etc. derivatives of our function f. So we've got f prime of t would be I beta e to the I beta t, right? Just using the chain rule on that. And then we can take a derivative again. And now we would get another I beta that comes down. So we have I squared beta squared e to the I beta. We do a third derivative, right? Every time we take a derivative, it's like multiplying by another power of I times beta. And just to take this out to the extreme here, let's take the fifth derivative. So these derivatives are fairly easy to calculate just using the chain rule. And then we can use some properties of the imaginary number to simplify things that look like this, to simplify the I raised to these different powers. Any questions about the derivatives so far? Okay, so then we can simplify this. So, well, this one is as simple as we can write it. For this one, what do we get when we take I and square it?
-1.
We get a -1, right? So I is defined as the square root of -1. So if we square it, then by definition, we get -1. So that I squared, we can just replace with -1 times beta squared e to the I beta t. And then therefore, I cubed is just minus I, right? It would be I squared times I. And what happens is we get some cyclic behavior in powers of I. So now we've got minus I beta cubed e to the I beta t. And then if I multiply by I again, what do I get when I have I to the fourth?
1.
We get 1. Thank you. And then we start to repeat. So I to the fourth, we can think of as I to the fifth, we can think of as I to the fourth times I. And since I to the fourth is 1, I to the fifth is also equal to I. And I think at this point, hopefully, you kind of pick up on the pattern of what's happening with the derivative and how we get this cyclic behavior in powers of I, so that each of our terms are going to either be imaginary I times something or real, not have an I in them. Okay, so then let's use all of these derivatives now to construct a Taylor series for this imaginary exponent. So we would take f of 1. And so if I plug 1 into f of t, then what do I get? Excuse me, if I plug 0 into f of t, what is f of 0? I'll accept fingers as answers. Is 1. Thank you. So f of 0 is 1. So now we've got e to the I beta t is equal to f of 0 is 1. And then f prime of 0, if we evaluate this at 0, we would just get I times beta times 1. So f prime of 0 is I times beta all over 1 factorial, which is just 1 times t. That takes care of that one. And then for this one, we could get f double prime of 0 would just be minus beta squared if I evaluate that at 0. So I get minus beta squared times t squared. And we can continue on in this process. So any questions on what we're doing here? And so let me just then write out the next bunch of terms. So then we would get plus beta, excuse me, we get minus I beta cubed all over 3 factorial times t cubed, and then we would get plus beta to the 4th over 4 factorial t to the 4th Got one. So that would be our 5th order term, and then I'll just stop with the 6th one. So in any case, you can see we've got a pretty predictable pattern that we're observing here. And if we group the real terms that I'll circle in red, so that doesn't have an imaginary number in it, that doesn't have an imaginary number in it, that doesn't have an imaginary number in it, and so on, what we can see is that all of the even powered terms of t are real. So I can group all of those together. So we get something that looks like this, which hopefully looks a little bit familiar. And then we have a bunch of imaginary terms, which are the remaining things that I can pull in I out from each of those. And that would leave over here, we would just have beta t. And then the next term would be minus I beta cubed, 3 factorial t cubed, plus I to the times beta to the 5th over 5 factorial times t to the 5th, and so on. Okay, so we've taken our Taylor series, which consists of even powered t's that are real and odd powered t's that wind up being imaginary. And I split them up, so I've got a real part and an imaginary part. Does anybody recognize what this part over here looks like? This is the Taylor series for what type of function?
Cosine function.
Yep, that's exactly right. So this is exactly the Taylor expansion of the cosine of beta t. And then all of this stuff over here, what do you recognize that as?
Sine.
That is the sine of beta. Yep. The sine is an odd function, and that's why we have odd powers in the Taylor expansion for the sine. So here we've got this result that when we take e and raise it to an imaginary power, we actually get a complex number that looks like cosine of beta plus I sine beta t. And this will explain why we saw some of the sines and cosines as solutions to some of the examples we were taking a look at already. So this result is what's called Euler's formula. So Euler's formula tells us that e to the I beta t is cosine beta t, I sine beta t. So if we have something like e to the alpha plus I beta t, we can write that as e to the alpha t times e to the I beta t. So the e to the alpha t comes from this part, and then all of this stuff comes from Euler's formula. Okay, any questions? Okay, so just to back up, When we were working with the differential equation where we had complex roots, we had something like this as our root. And so using the bullet above, we might think that, okay, one solution might be something that looks like y is equal to e to the 3t times cosine. In this case, my beta value is 1, right? Since I have 1 times I. So at this point, we could say that this exponential that I found over here, we can write it as e to the 3t cosine t plus I sine of t. And that should be a solution to the differential equation. And in fact, it is a solution to the differential equation. The problem is we want to find real solutions. And what I've found here is a complex solution. Okay, are there any questions? Okay, well.
It's plus or minus I. Does that come into a consideration? Is this only one part of the solution?
Yeah, and then we would have another one, which would be, right, we could think of beta as being -1, and you could have cosine of minus t. Cosine of minus t, because cosine is an even function, cosine of minus t actually is equal to the cosine of positive t. But that's not the case for the sine. The sine of minus t, because the sine is an odd function, equals minus the sine of t. So yeah, they're different, but still somewhat similar looking solutions, yeah. But I'm not happy with that solution again, because I want to find a real valued solution. And this one is complex. So how do we get rid of I? We had differential equations typically look like a, and what we have, if we have an I in our formula, then what we're giving is not a real valued solution, but a complex solution. So here's a little theorem in question 2 that we can prove to show how we can use complex solutions to generate real solutions. So let's say we've got a differential equation of the form. So let's kind of keep this on the side. So what we've got here, let's assume we've got a complex valued solution, which we do have for the example that we're kind of stuck on. And what we're asked to do here is we're going to show that the function p of t and the function q of t, right, ignoring the I, are each solutions. So if I want to show that p of t is a solution, what that means is when I plug it into the differential equation, I should get 0. So let's start with what we know, which is when I take this and plug it into the differential equation, it satisfies that differential equation. So in order to plug that solution into the differential equation, we need to know what the derivative of z is. And we take derivative of complex things just like we do real things. So I would take the derivative of the real part and then add it to it, I times the derivative of the imaginary part. And so we've got first and second derivatives, and now plugging these in to the differential equation, we would get A times Z double prime. So that's going to be P double prime plus I Q double prime plus B times P prime plus I times Q prime plus C times P plus I Q. And I know that equals 0 because that's the one piece of given information that we have, that this is a solution. And what I'd like to do is show that P of t and Q of t are each solutions themselves. I forgot a prime on a B of Z. Thank you. Over here. Yes, thanks. Okay. Any thoughts about what we can do with this equation over here?
Can we group the things together, the P's and the IQs together, and then pull an I out of the Q's?
Yeah, so let's group the real and imaginary parts together. So we've got an A P double prime plus B P prime plus C P. And that takes care of this term, and that term. And then I can add to that I times all of the imaginary stuff, which is A Q double prime plus B Q prime plus C Q. And I know that all of this is equal to 0, right? Because again, we were given Z is a solution. And so let me just say that if you have a complex number which is equal to 0, that means both the real and the imaginary parts have to be 0. So here's the real part. That comes from matching up the real parts. And then we also have that the imaginary part, which is A Q double prime BQ plus C times Q, is also equal to 0. And that comes from checking that the imaginary term also needs to be 0. So even ignoring the I over here, what we can see is that individually, I guess our equation is with respect to Z, that Z equals P of t is a real solution. And Z equals Q of t is also a real solution. Okay, intense here. We're doing a lot of Taylor series and kind of doing a little proof over here, actually. So any questions? Okay.
Yeah,
so
as you said, Q
yeah.
of t is a real solution. We're just ignoring that it's multiplied by the I.
That's right. So we just showed, even if we ignore the I, like we know we have this term over here, or excuse me, we have this term over here, but we know that the thing that's multiplying by the I, that has to be 0 if overall that complex number is 0. So that tells us that the term multiplying the I is 0. So that tells me Q of t itself has to be 0. So let's see what that looks like for the example that we were working with. Okay, let me just add a page in here. Okay, so I think we had like e to the 3 plus or minus I. T was our root was 3 plus or minus I, right? So that means something that looks like e to the 3 plus or minus it would be a reasonable solution. So let's just consider the 3 plus it. And using Euler's formula, we've got that this would be e to the 3t times the cosine of t right? So using Euler's formula, we would know that is a solution. And let me just distribute that e to the 3t. So that would give us a complex solution. And then from the previous result, we know that P of t, which is the real part, is a real solution. And so is Q of t. Okay, and so now we can ignore the I, and we've got two real solutions. And what we showed last time, if we multiply each of these by a constant, that doesn't change anything. And then when we add them together, we're going to get the most general solution. So that's how we handle complex roots. You don't need to go through this entire proof every single time. I wanted to just show you where this formula comes from rather than just spring a random formula on you. Any questions?
Does this only deal with the one root though? What about the negative?
Yeah, so let me just say that you can use the fact that cosine of t equals cosine of minus t, so that's not going to change anything. And you can use the fact that the sine of minus t equals minus the sine of t. So it's almost like those two solutions, you can kind of express them in one solution and just know that the C2 kind of takes into account that when we plug in minus t, we just get a different multiple of the sine of t. So once we get a solution that has two arbitrary constants, then we're done. So I could have done the same sort of thing using the other root, and we would have gotten the same sort of point here, except we would have a negative in front of the C2. So the short question is, once I just need one of those roots to generate the most general solution.
So when we're solving with initial constants, there'll be one value of C1, but two values of C2?
Nope. You'll still have two initial conditions. You'll plug them in, and you should find a unique value for C1 and a unique value for C2.
But it changes with the negative sign.
So no, because this is the general solution over here. So if I use this as my general solution, I'll get a value for C1 and C2. And if instead I want to use this as my general solution, this minus sign can get pulled out and just gets absorbed into an arbitrary constant. So what I'm saying is the most general solution is going to look like some arbitrary constant e to the 3t cosine of t plus some other arbitrary constant e to the 3t sine of t.
Okay.
Okay, so let's kind of summarize all of these results down here and then take a look at an example. So if I'm trying to solve a problem like the one in number 3, right, obviously initially you don't know whether the roots are real, repeated, complex, or whatever. So kind of always the first step here is going to be set up the characteristic polynomial. Then we solve it. And then depending on roots, whether they're real, imaginary, repeated, we're going to take the solutions that we find to the characteristic equation and plug them into the general form of the solution. And that general form of the solution is going to differ depending on, again, whether our roots are real or repeated or imaginary. So if I find 2 distinct real roots, we've already discussed that that one would look like this. If we have 1 repeated real root, last time we discussed that that would look like this. And so now, that's funny, there's like a slow delay between my writing. Here we go. And then if we've got an imaginary root of the form alpha plus I beta, then you don't need to go through that whole long process that we went through. You can just go directly to the fact that it's going to look like e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. So it's just knowing what to do with the roots. Sorry. It's going to appear magically in a second, I hope. Okay, let me try and re-share this. Okay, that's what I was writing before. So if we have the complex solution, then we just take the real part and that goes in the power, and then we take the beta from the imaginary part and that goes in to the trig functions. But notice there is no I anywhere in the solution. So this is a real solution. Okay, that whole start here was just putting in the work so that we can now use this shortcut for generating solutions when we have complex roots. And these trig functions shouldn't be surprising you out of anywhere because we've already seen that there are cases where we get sines and cosines as solutions. Any questions?
Can you talk again about how the plus or minus beta I gets reabsorbed?
Yeah, do you mind if we talk about that?
Yeah, after class.
Yeah, sure.
So right now, if it's not in one of these 3 forms, we don't know how to do this.
This exhausts all of our possibilities. So if you have a quadratic equation, either you have two distinct roots, one repeated real root, or complex roots. So we've exhausted all of these possibilities. Yeah, there shouldn't be any other possibilities. So now we should be able to, we can definitely solve any homogeneous differential equation of that type. So maybe I'll just ask you to work through this one, and then we can discuss it. I don't think, I'll send you out into breakout groups for some of the other problems, but this one I'll just let you work on by yourself, and then we can compare our results. And if you have any questions about solving this one, you can chat me privately, and I can get back to you. So one thing that's really nice, so this is all contained in section 2.2 of the reading materials, is that solving these differential equations is something that, right, you do in like a algebra or pre-calculus class. So all we really need to do here is solve a quadratic equation and then just know what to do with the roots afterwards. So I'll just kind of go through some here just to make sure if you started off in the wrong direction, right, the characteristic equation here would be r squared plus 2r plus 17. And then what are the roots for that characteristic equation? Anyone get the roots?
R equals -1 plus or minus 4i.
What do you guys think? Okay, I'm getting some head nods.
Is it 4 or 8i?
It should be 4. That's right. And so just be careful that when you have right, the quadratic formula, and you're dividing by 2, that means you need to divide that by 2 and that by 2. So you've got that, right, you probably have like square root of -64, which becomes 8i, and then you divide that by 2, and it becomes 4i. Yeah. Okay, and then the idea here is, okay, I've got complex solutions, so now I know that that should go into something that looks like this. So my value for alpha is -1. It does matter that that's negative. That's really important. The value for beta in this case is 4. And that would be our general solution. And I will just caution you that when you have initial values given to you, typically it's going to be, here's the value of y at time 0, and then here is the value of y prime at time 0. Finding y prime, you need to be really careful with these. There's product rule, couple chain rules, and so on. So when you're finding y prime, just be really careful about that. And I should change this to an x, because that was our differential equation. Okay, so any questions about how we can deal with these imaginary roots? And that was really the main point of that discussion. Okay, so the next couple of questions are going to deal with a series of differential equations that are modeling what's called the mass spring system. So let me show you what that looks like in general, just to get a sense of the mechanics in the background. So you've got a mass, which is this, can you guys see that, this screen? Making sure, yeah, okay. So you've got this mass, which is the green thing, and then you've got this spring in blue, and it's attached to this, a wall in this case, which is red. And then you can think about, well, what happens if you pull or push this mass in some way? So what happens is there's like an equilibrium position for the mass, right? You can just imagine if the spring is in its natural position, and if you push it in and then let it go, right, you would expect it to go back and forth like this. If you stretch it out and then let it go, you would expect the same sort of thing. So here, if you play this out, you can see this is what happens to the spring, not very exciting, and you can see what the solution looks like over here. So this system of a mass spring depends on three parameters, which is what is the mass of this green thing, how stiff is the spring, like what is the spring made of, that's called the stiffness coefficient, and then how much friction is there on the surface that we're rotating this mass back and forth over. So this equation on our worksheet is from that situation. And that's really where studying these systems came from, was studying these mass spring systems. So in this example, in general, we have some spring over here. And so y is denoting its displacement from its equilibrium. So let me just say y equals 0 means it's at its equilibrium. And y greater than 0 means it's to the right of the equilibrium, and y less than 0 means it's to the left of the equilibrium. So maybe our equilibrium might be right here. If our mass is located over here, its y value would be positive. And these systems are governed by equations that look like this. And in case you're curious, we can get into this at a later point. I can put up a video that kind of shows where these, how you can derive these equations. But it really comes from Newton's second law. Where A is the mass of the spring, B denotes the damping, which is another way of saying the friction of the surface, and C is denoting the stiffness. So you can see this mass times acceleration sort of thing is where the second law, Newton's second law, comes in. So these mass spring systems are governed by equations that look like this again, where the A, B, and the C come from physical parameters of this system. And in this case, all of these values, A, B, and C, are assumed to be at least greater than or equal to 0. So these are not negative valued parameters. So that's the model that we're working with here, in case you're kind of curious. And what these questions are asking you to do is just think about what happens when we change the damping coefficient a little bit. So what happens when we add friction or take friction away? So really what's going on here is in part B, it's asking you to solve the differential equation, right, when you substitute B equals 0 into that equation. So this would be the case where there's no friction whatsoever. And I think it's really nice to take a look at an example like this because we can see when we attach meaning to this value B as friction, why when we add friction, does that change the behavior of the solution? And why are our solutions going from trig things to exponential things? So there is some physics going on in the background, but what you're ultimately being asked to do in this problem is just solve a couple of second order differential equations when we change the value of B. How does that affect the solutions? Okay, any questions? Okay, well then I will break you up into groups, and the goal here is to go through question 4. It's long, there's a lot of parts, so however far you get, I don't expect to get through all of it, but please help each other out, bring everybody into the discussion, and then I'm gonna leave you guys to work on these for 15 minutes, and then we'll use the last 10 minutes to compare answers and kind of summarize the work that you've been doing. Okay, well, welcome back to the main room, everybody. So let's take a look at how far you might have gotten in this. I think certainly we'll get through some of this, and then this is where we can start things on Monday. Yeah, I don't think I put any mass spring questions on this homework. Does that sound right? Don't think so. But okay, so let's take a look. Question A is asking us to make sense out of these initial conditions. So remember, y is our position relative to the equilibrium. So if y of 0 equals 1, then what does this mean kind of physically about the system? And want to share what came up in your group?
So we found as so we found for the particular solution that y equals cosine of 2t. And
Okay.
so as t approaches infinity, it'll oscillate.
Okay, yes. That's part B. Yes, that's all great. So yeah, sorry, I'm in part B, so that makes sense but I ran out of room for part A. So I just want to make sure we touch on part A. So this initial condition that at time 0, y is equal to 1, what's the practical meaning of that?
It's not at equilibrium.
It's not at equilibrium, and in fact, where is it located?
It's getting pulled, so it's away.
Yeah, that's right.
To the right.
So it's 1 unit to the right. And in this case, I'm not sure if we have units of distance here. Yes, I guess not. So we'll just say that at time 0, in other words, initially, mass is 1 unit to the right. And secondly, what would the derivative being 0 tell us? So if y is our position, what does
the
derivative?
velocity starting out is 0.
Yeah, exactly. So the derivative is telling us the velocity. So initially, at time 0, okay, so it's not being pushed or pulled. So it's like we're just pulling it 1 unit to the right and then letting it go, as opposed to pulling it 1 unit to the right and then pushing it back towards the left or pushing it towards the right. So we've got that at time 0, we're 1 unit to the right. So if we're plotting our position versus time, sorry, I should have time over here. Okay, all we know is at time 0, we're located over here, and the slope should be 0 at that point because its derivative is 0. Okay, and so to solve this differential equation, so any questions about interpreting those conditions, initial conditions? Okay, so then our differential equation here is y double prime plus 0 y prime plus y. I think there's like a 4y here. Should be a 4 over here. Is equal to 0. Yeah, that's right. And so you could solve this in different ways, but the characteristic equation would be r squared is equal to 4. So we've got r squared is minus 4, and thus r is equal to plus or minus the square root of minus 4, which is plus or minus 2 pi. So with that said, since Kirsten, I think you were sharing what you did on part B, so then what was the general solution that you got based on those roots?
So the general solution was y equals c1 cosine of 2t plus c2 sine of 2t.
Okay, so here the alpha value is 0, so we actually have like e to the 0, which is 1 times cosine of t, and e to the 0 times the sine of 2t. That's right. So we get just these purely trig functions here, no exponentials. That's right. And then using the initial condition that at 0, we should get a position of 1. That tells us that C1 plus C2 is equal to 1. And then using the condition that at 0, we have no initial velocity. What was the resulting equation that you got for the C's there?
So we got that c1 is equal to 1.
Yeah, so so if you're kind of setting this up to find the C1 and the C2 values, we would use 1 to get one equation, and then using this, we would get a second equation, right?
Wouldn't the first equation, so if we take sine of 2t.
Oh, yes, sorry, you're right.
Okay.
Yes, sine of 0 is 0. Yeah, so we get C1 is 0, and then, excuse me, C1 is 1, C2, using this condition down here, you could check that you should get that C2 is equal to 0. So that means we have a particular solution, which is 1 times the cosine of 2t. That's right. And so what happens to this as time goes on, the cosine function is just going to oscillate back and forth between 1 and minus 1. And since at time 0, our velocity is 0, that means we're starting off at the max value at 1, and the slope there is 0. So here, as t goes to infinity, what we can see is the mass is going to oscillate back and forth forever. Okay, and that hopefully makes some intuitive sense based on the system, which is telling us now if we're doing this on a frictionless system, then it's just the spring is the only force acting on it, and it's just going to keep bouncing back and forth and back and forth. So any questions about the solution to part B? And this is what we would call in part B the undamped oscillator. So we'd say this is undamped because there is no friction. And then next time we'll take a look at what happens when we add some friction. So if you got to some of those solutions, we'll make sense out of that. But let me just kind of go back to this little demonstration just to see what our solution looks like here. So over here, I can enter all of the information about our system. So we have an initial position of 1. We have a spring constant of 4. I think that is accurate. And in this case, we had no damping. So I'm going to set that to 0. Our mass is 1. And then we'll worry about the forcing at a later time. But here you can see what's happening to the solution. And this is mimicking what we got in our solution. So we're seeing that we start off at 1, we have a cosine function, and it's just bouncing back and forth between its maximum displacement and its minimum displacement, and it's not going to slow down as time goes on. So what I want to take a look at, what we'll take a look at next time, is what happens when we start to add, not mass, but when we start to add some friction to the system. And you can see we'll get some different behaving solutions. And that's going to relate to what happens when we have real roots, repeated real roots, or some other sorts of things. Okay, so thanks everybody. We are out of time, so I'll stop here and we'll pick up next time with part C. And then over the weekend, you've got homework assignment open. That's due on Monday, and I'll get another quiz up probably sometime tomorrow. That will be due on Monday. And you've got that survey as well, which would be great to get some of your feedback on that. So if you have any other questions, feel free to stick around. Otherwise, if I don't see you before Monday, have a nice weekend.
Thank you.
Yep.
Thank you.
Okay, Abraham, what's going
So
on?
I think I understand it maybe a little more. The negative, I get how the negative comes out and the cosine doesn't get touched. But to me, it seems like there's two plus or minus b's, i's
Yeah.
in the C2 term. That was my main question.
Yeah, you're right. So let's just be a little bit more careful about that. You're totally right. So so let's say we've got like R was I don't know. Let's just make something up. Say we had.
Are you writing on your screen right now?
I am. let me share that with you.
You seem really intent on your task.
I haven't written much, so it's okay. Okay, and then let me share.
Also, I really appreciated the definition of Euler's formula. I think it was shared with me, but it never was shared well.
Yeah, so it's just a nice application of Taylor series.
Yeah.
Okay, so this is what I wrote over here. So let's say we find like our root is 2 plus or minus 3i. And from Euler's formula, that's right. Just to kind of go through this really carefully, we would have, right, there's one solution, and this would be another solution.
Yeah.
Oops. Let's turn my iPad off. Okay. Good. So this one we can write as like e to the 2t cosine of 3t plus e to the 2t sine of 3t. So let's just say, okay, there's one of our real solutions, right? So I'm going to multiply that by C1, and then I'm going to add to that the other solution, which you're right, is technically a little bit different. We should have a minus inside of there. So is this kind of what you were tackling? Okay. So then we've got C1 e to the 2t cosine of 3t. And I'm just going to group the sines and the cosines together. And then from the other solution, we have a C2 e to the 2t cosine of minus 3t.
That would change to positive 3t.
Right, which is the same as cosine of 3t. So really this part we can write as C1 plus C2 e to the 2t cosine of 3t.
Yeah.
And C1 plus C2 we can just call some arbitrary, that's just some arbitrary constant B1. And then for the signs, we need to be a little bit more careful. So this would be changing the sign now. So when I have a negative inside of the sign, that actually is equivalent to minus the sign of its positive value.
Yeah.
And so this we can group together. And I can just call this some other arbitrary thing. And so that's why we can group these things together and just really write it as some arbitrary thing times the cosine piece plus some other arbitrary number times the sine piece.
Okay. So it's like those two constants, the plus and minus, are kind of shared. I'm saying like in the distinct roots one, we had a C1 and a C2 corresponding to each distinct root, basically. And then with this one, it's kind of like the C1s and C2s are shared. You know, it's not like the plus or minus 3i has one distinct root for the plus and for the minus I. It's
Right.
kind of like they're shared together.
Yep.
Between the C's and this. Okay.
Yep.
Right.
Yeah, and so I kind of bypassed this part of it, but yeah, that's technically why that happens. Yep.
Cool. Thank you.
Yep, no problem. Did you have a
good day.
question, Kenneth?